Hello class, welcome to the Chapter 6 Jump video. To begin, you should pull up the Chapter 6 Jump handout, and to begin, we are looking at the information that came from your notes, slide 34, and specifically we're going to look at our second data set. Now there is no textbook data file, so we are going to have to enter this file or data set in manually. So I'm going to go ahead at this point, open up Jump. Go to File, New, Data Table. And I'm going to do as I've done in the previous videos where I'm going to kind of split my screen so that I can both look at the Jump handout and take a look at Jump itself. So for the first column, we are going to have our sample. And we are going to have a series of 1, 2, and 3. Now, I could just type this in directly by hand. I'm going to actually go about it a bit of a different way. So by going to column info, if I select initialized data, I can select sequence data, and I'm going to want to go from 1 to 3 in a step of 1, and we want to repeat each value 5 times. I'm going to select OK, and then that will automatically give me the information I want. And as we can see, this data is nominal, so I'm going to click our blue triangle on the left and change it to nominal. So I'll have a red histogram, and now I can select my response data that's set to output. So I'm going to change the column name. And now by hand I will type in this data. All right, perfect. And so notice we have this in a stacked format, which means we have a series of the 1s, 2s, and 3s. The first objective we are going to have now that we have our data as we desire it to be is to create those side-by-side box plots. So in order to do that, we are going to go to Graph, Graph Builder, and we are going to drag and drop sample to the x-axis, set output to the y-axis, and then we are going to select the icon that says box plot. And there we have it. We have our box plot that we desire, and we can compare our variations in our two samples. So we can see that sample 2 has the most variation. Sample 1 is the most symmetric sample by looks of it. We have an equal number, at least on the box, if not the whiskers. So that's one way to do our box and whisker plots. Now we can examine how to do the overall F-test, which is something that is pretty important for us to be able to do. For this, we go to Analyze, Fit Model. Our sample is our model effects, which we can select Add, and then Set to Output is our Y. We will select Run. If I scroll down, we can see that we have our analysis of variance. And if we are curious, we also have this least means squared table that will give us our averages per sample, which can sometimes be useful. Now still continuing with our jump handout, because that was the end of slide 1. Now if we look, we can say if we, so we looked at page 1, now we're going to examine another page which corresponds to slide 56 in our chapter 6 notes, and we use the data file 6.29. So I'm going to exit out of what I've done so far, including the JMP handout, and I'm going to open up table 6.29. Nope, okay. So I'm going to have to do it the old-fashioned way, which is go to our book data sets in eCampus, chapter 6, and table 29. Perfect. And so what should come up is our data for our mice example. So again, I'm going to take a second and organize the screen. And what we would like to do is, once again, we'd like to get our ANOVA table. So we are going to go to Analyze, Fit Model. Time was our response. Color was our effect. And we are going to select Run. Scrolling down, we have our ANOVA table. We have that least mean squares table that I discussed before. And I am curious, if we select our red triangles, we have different options we can do, such as creating normal plots, custom tests, we can perform multiple comparisons. If we wish to show confidence intervals under regression plots, we can do that as well. Row diagnostics, which can give us various tests such as studentized residuals, plot normal quantiles, the press statistic. Under save columns, we do have some options such as the mean confidence interval, individual confidence intervals, residuals, etc. All right, so taking a look at this, I want to make sure I haven't left anything out. So since the textbook data file for table 6.29 is in the stacked format, just run the analyze fit model, same to the previous page. To obtain the ANOVA and least squares mean table below, least squares mean table lists the means. This has come up automatically. The true distribution and analyzes of the time responses are below. The first below center is for all 15 time responses, where the second is by color and has the same sample mean as our least squares mean. So if I recall, how we can get to those two windows is if we go to Analyze Distribution, color would be for by color, or excuse me, I just did that wrong, by color, and time is our Y column. Sorry about that. So time is our Y, by is our color, select OK, and we can get our typical summary statistics. And we can do this per each color if we are so interested and we need it. Next, it says that we have an option for an exercise, which is to use the distribution reports above, center, and right to compute the series in the ANOVA table with the formulas by hand. I'm not going to do this in this video, but I would encourage you to do it for extra practice. Next, let's talk about how we can do the orthogonal contrast. So in the right column of the fit model report, so if I bring up our fit model report, under color option, we have the option to select LS means contrast, which we may select and then perform our necessary contrast. Now for us, we originally did a contrast where we compared the black versus the red and green door. That was one contrast we performed. We also considered the situation where we compared the red and green door. And if we select both of those options, we can get our test details, where we can get our estimate, standard error, the t-ratio, and our p-value and our sum of squares statistic, which will give us our necessary information. So the p-value and t-ratio gives us a test of whether or not there's a significant difference in our contrast. So for the first one, whether there's a significance difference between the black door and the red and green door, which we can see is the case. And then also when we compare the green and red doors, we can see that there's even greater significant difference. If we are trying to do our ANOVA table with a contrast in it, these are the sum of square statistics we would need. So in the event that you need to perform a orthogonal contrast in the future, that is how you can do it using JMP. Now, as I said before in our slides, sometimes we don't know what our pre-planned comparisons are, so instead we perform post hoc comparisons. In order to do that, we are going to still select this red triangle, where we are going to instead select LS means students T, and this will do a comparison of all of our options. So it'll compare the black to green, green to red, green to black, all of those options. And what is really important about this result is right here is this table, particularly this middle part where we see this A in one column and two B's in the second column. And what it does is this table pretty clearly displays the relationship that exists between the doors, specifically where the differences lie. So what this is saying is that there is an insignificant difference between the red and the black door, but there is a significant difference between the green door and the other two doors. Notice that they're in two different columns and represented by two different letters. That is a visual representation on how we have our differences. We can also read that same information from the table, but I think this visualization makes it easier. Finally, the last part of this we want to look at is the simulation. And it says in a new JMP table, so I'm going to exit out of this. So we got what we needed out of our table 6.29. Now at this point, we'll open up a new table to perform a simulation. So I will go to File, New Data Table. Going to adjust as the format I like. So in the new data table, we are going to double click on the header of the first column and define this as not as, we'll just say, we'll call this our sample. We are let our data type still be numeric, but we are going to change it to be nominal data. And as I did in one of the previous examples, we're under initialized data, we're going to select sequence data. And we want to make a set of 5 ones followed by 5 twos, ending with 5 tens. So we are going to want to go from 1 to 10, steps of 1, and we want each of these values to be repeated 5 times. I'm going to select OK. Very good. Now I'm going to do our response. So in order to do this, I'm going to double click the header on the second column. I'm going to call this response. And now for this, I would like it to be a random sample from the standard normal distribution. So under initialized data, I am going to select random. I'm going to select the option that says random normal. And from here, I'm going to select OK. So I have my responses that are randomly generated from the standard normal distribution. Using this, we can actually go ahead and reanalyze this as we did in our post hoc experiment. So we can go to analyze fit model. Our responses are Y. Our sample is our model effects. We can select run, and we have our overall F test, which we can see is insignificant, which should be expected since we have randomly generated data. We shouldn't necessarily see a correlation, but just for fun, let's check out the LS means students T. And what we can see here is that we have a single column, all of A's, which is saying each of our response samples, so samples 1 through 10, are each insignificantly different from each other. Which, if you have randomly created data, theoretically you really shouldn't have any sort of pattern which would indicate a significant relationship. Okay, so let's move on at this point and talk about how we can assess our ANOVA assumptions. So first we can talk about how we could check for our normality assumption. So in our upper left of our fit model report, which I exit out of, so I'll have to quickly recreate. So analyze fit model, response for their Y, sample for our model effects, select run. So as it said before, we are going to click on our red triangle under response, and we're going to select the option for save columns. And what we're going to save is our predicted values and the residuals. At this point, I'm going to minimize. And notice we now have our options for predicted and residual responses. Now we can go ahead and make our histogram. So we can go to Analyze Distribution. In this case, our residual time is our Y. If we select OK, we should hopefully have a normal histogram if our data follows the normal distribution. Next, we can assess our equal variance assumption, which we can use with specifically the mice data. So I'm going to pull that up again just to give it a little bit more realism. So if we go to our table 629, let me get this screen how I want it to be. And just for funs, let's go ahead and actually redo our normality assumption, this time with the mice data. So if I go to Analyze Fit Model Report, time is our Y, color is our effect. I want to save the column, so red triangle, save columns. I wanted the predicted values and the residuals. Minimize, so I want to go to Analyze Distribution. Residual time is my response in this case, and this will give me my histogram that I evaluate to assess the normality assumption. And this does have a normal-ish shape, which, and I say in that in the sense that we have a very small sample size of 15, so sometimes you have to make leeway when you have a sample size less than 30. So I can assume at this point that it is probably mostly normal. Now, in order to assess our equal variance assumption, we are going to go to Analyze, Fit Y by X. Time is our response. Color is our factor. I'm going to select OK. And what we see here is really our analysis of our 3 color doors and their variability. Now I could, if I wanted to, do what we did in the previous slides and make histograms, but we can also perform the Levene's test by selecting the red triangle, unequal variance, and we will get the Levene's test in a table. And again, in this case, we want our p-value to be large because the null hypothesis states that our variances are equal. The alternative hypothesis states that our variances are unequal. And ideally speaking, we want our variances to be equal. We also could have created a residual plot, but that isn't not necessarily in this case. We don't need to necessarily do it because we can get a pretty good idea of it just looking at our time by color. If we examine each of our colors and the spread, we can see that while the spread is not exact, they are pretty close, particularly the black and the green, which is why we would say that their spread, their variability is rather consistent or equal. So the exercise asks us to explain why the results for Levene's test agrees with the above plot, and I kind of just described that. We can see that each color has approximately the same variability. The next exercise asks us to describe on slide 74, it says, as described on slide 74, we want to validate that you can conduct the Levene's test and get a p-value of 0.5384 by performing ANOVA on the absolute values of the residuals. I'll leave that to you as well as the rest of the exercise. If you have any questions on it, please ask me and I'd be happy to help you out with it. This will just give you a way of practicing how to perform a transformation, which isn't something we necessarily focus on in this class, more of just that you know it's a possibility. So this is just really just good practice for you. And that's about it for this jump video. If you have questions, as always, please send me an email. Have a good night.